Okay, thank you. Welcome to the EE Colloquium. I'm very pleased to have the opportunity to introduce Athina Petropulu. She's a colleague that I have known for many years in the Signal Processing Society. She's one of the leaders in our community. Athina has been involved in about as many IEEE things as you can imagine. She was a chair of a very successful ICASP in '95, and so they got her to then become the VP of conferences. We've served together as editors on the Society's publication board. She edited our flagship journal, The Transactions on Signal Processing. She's won several paper awards, and she's served on the Board of Governors, and she's been honored with a Presidential Fellow Award, precursor of the very distinguished PCASE NSF Awards. She's also currently, or just about to start a term as one of the IEEE Signal Processing Society Distinguished Lecturers. So she's had a very distinguished career in terms of signal processing research, focusing in the area of signal processing and communications. She's also an accomplished academic, formerly the department chair at Rutgers University, and currently she's on sabbatical, enjoying a well-earned almost rest, working at USC. So without further ado, I'm very happy to welcome Athina to our colloquium.
Thank you, Mary, for this nice introduction. It's my pleasure to be here. I appreciate the invitation. So today I'm going to talk about the topic of spectrum sharing between communication systems and radar systems. And what I'm going to talk about is basically the PhD work of my student, Bo Lee, and contains also contributions from the work of my other students, Sanxiao San and Colloquium. They're all PhD students at Rutgers University. So the outline is, eventually I will be talking about spectrum sharing between MIMO radar that use sparse sensing and MIMO communication systems. And before I get to that point, I will need to introduce what is MIMO radar using sparse sensing, so I will spend some time on that. And then I will discuss the motivation for studying this sharing, because of some changes that are about to happen in the way the spectrum is used. So let me start introducing MIMO radars before I get to MIMO radars with sparse sensing. You may have heard about phased arrays. Phased arrays is a configuration of transmit and receive antennas. And all transmit antenna elements send out the same waveform. But before transmitting it, they multiply it by these weights. And by adjusting these weights, a focused beam can be created, focusing in a particular point in space. So by changing these weights, we can change the direction of the beam and scan the entire space. And if there's a target there, there will be a return that will be received by the receive antennas. The receive antennas send their measurements to a fusion center, and the fusion center detects the target and estimates the target. MIMO radars are a little bit different. The transmit antennas, still you have a configuration of transmit and receive antennas. The transmit antennas transmit independent waveforms. So there's no way to create a focused beam if you transmit independent waveforms. But the good thing is you don't need to scan the space by changing weights. Once you transmit these independent waveforms, you illuminate the entire space. And if there's a target there, there will be some returns that will be captured by the receive antennas. Again, the receive antennas send their measurements to a fusion center that makes the decision. So the good thing is less scanning time. It has been shown that MIMO radars give higher resolution than phased arrays with the same number of elements. But they have smaller gain, smaller SNR, because you don't create a focused beam. There are two kinds of MIMO radars that are collocated, where all transmit-receive antennas are close together, so they see the same view of the target. And there are distributed MIMO radars, where the antennas are widely separated, and each one sees a different view of the target. Each one has different advantages and disadvantages. In my talk, I will be focusing on the first class, where the antennas are closely spaced together. Nowadays, there's a lot of interest in networked radar. Radars that can be deployed on moving vehicles, on maybe the backpacks of soldiers, maybe on drones. So these radars will act as the antenna of a distributed radar system. There are times where the antennas will be connected via a wireless link, the receive antennas. So when they need to send the information to a fusion center, they will have to use that wireless link. And in order to achieve reliable surveillance, you need a lot of data to collect and communicate a lot of data. So there is a communication power and communication bandwidth issue involved with such scenario. So to deal with this issue, it has been proposed to use compressive sensing in the context of MIMO radars. So the received antennas will perform compressive sensing and send a smaller amount of data to the fusion center that will use this data to estimate the target. So in the past, we have developed a MIMO radar with compressive sensing that exploits the sparsity of the target scene. The target scene is sparse in the Uncle Doppler range domain. And based on the measurements that the receive antennas receive, we formulated a sparse signal recovery problem that estimated the targets. However, this approach fits a grid on space and requires the targets to be on the grid, which might be a little bit sensitive if the targets fall between grid points. Our most recent work uses MIMO radar with sparse sensing and matrix completion. And it's this later work that I will be describing today. It appeared, most of what I'm going to talk about today, it appeared in the September issue of the IEEE Transactions on Signal Processing. So I'm moving on to MIMO radars using sparse sensing and matrix completion. A little bit of background of what is matrix completion. So you have a matrix, and you can observe only some of its elements. There is a theory that says that under certain conditions, you can fill in the missing elements. This is called matrix completion. Mathematically, what this means is how the matrix is completed is solving this minimization problem. So you're looking for a matrix that has the smallest possible rank and fits the observations that you have. So capital omega is the set of indices that you observe. So you want to recover a matrix that has the same entries as the entries that you observe. And if you try to do that, this is a very difficult problem. Instead, we relax the problem and we try to solve a convex minimization problem, which is to minimize the nuclear norm of that matrix. The nuclear norm is the sum of the singular values. So if you minimize the nuclear norm, eventually you will find a matrix that has the smallest rank. If you have noisy observations, then the minimization problem is slightly different. You look for a matrix that has the smallest nuclear norm, and then the error between the observations and the estimates is smaller than some threshold. Now, about the conditions under which you can complete a matrix. Now, a key notion here is the notion of matrix coherence. Suppose that you do an SVD on the matrix M, and U and V are the left and right singular spaces. Then the matrix coherence for matrix M with parameters mu0 and mu1 is defined like this. We want the maximum of the coherence of U and V to be less than mu0, or the maximum element of this function is bounded by mu1. So the matrix coherence is given in terms of the coherence of the left and right subspaces, and the key role is played by these parameters, mu0 and mu1. But still, I haven't told you what is the matrix, what is the coherence of the left and right subspace. Okay, so this is the formal definition of the matrix coherence. If you look at the space that is formed by the singular vectors U, and you take the standard basis vector, it's a vector that has only one non-zero element equal to 1 and everything else 0. So you take that EI, the standard basis vector, and you project it on the space formed by the singular vectors. Basically, you're forming this function, this projection, and then you look at the magnitude of this projection. And this is the coherence of subspace U. Now, eventually, you will want this coherence to be small. So you want this projection to be small. A small projection, when you project the basis vector on this space, the projection will be small if the U's are dissimilar with this basis vector. So basically, this projection quantifies the similarity of the basis vector, the standard basis vector, to the singular vectors. That standard basis vector is the sparsest possible vector. It has only one non-zero element. So if you want this projection to be small, means that the singular vectors should be as dissimilar as possible to the standard basis vector. So they should be as less sparse as possible. So you want the energy to be uniformly distributed on these singular vectors. So this is the main idea of the behavior of the coherence in order to do matrix completion. You want the singular vectors to be as spread out as possible. And there is this theorem that says that if you have a matrix, N1 by N2, then if you have available M elements of this matrix, where M is greater than this function, now what is this function? This function contains the mu1, mu0, the coherence parameters, the rank of the matrix, and N. N is the maximum dimension of the matrix. So if you have M elements greater than this function, then you can recover the matrix with high probability using nuclear null minimization. So the smaller these parameters are, the fewer elements you need in order to do matrix completion, right? And the smaller the rank is, the fewer elements you need to do matrix completion. So in order to do matrix completion, the bottom line of this is that you need the matrix to have eigenvectors that have uniformly distributed elements across the vector and small rank. Now these parameters, the smallest possible value is 1. Now let's look at the MIMO radar scenario. You have the transmit antennas that transmit, as I said, independent waveforms. In most cases, these waveforms are orthogonal to each other. And here is a diagram of one receive antenna. Because the waveforms are orthogonal, this is the receive antenna array. So this is one receive antenna. Because the transmit waveforms are orthogonal, the antenna will use a match filter bank to isolate the contribution of its transmit antenna. So it will do match filtering with the transmit waveforms. And if there are empty transmit waveforms, it will get these empty views of the target. right? Each antenna will do the same thing. Now, the antennas will forward their measurements. These are the measurements to the fusion center. And the fusion center will formulate a matrix. So it will take the measurements of the first antenna, put them in the first row of the matrix, and so on. It will fill out this matrix. So if this is the data matrix that I just described, the Y, it can be expressed as some noise plus a delta matrix. And this delta matrix has a very special structure. It's the product of three matrices. The left matrix that is formulated it depends on the receive antenna configuration. This matrix depends on the transmit antenna configuration, and this is a diagonal matrix that depends on the targets. If you have the detailed description, it doesn't matter. Maybe I shouldn't bore you with the details. But the idea here is that if you have a large number of transmit and receive antennas and a small number of targets, this delta matrix will be a low-rank matrix. So this means that maybe it meets the conditions to be completed. So if it does meet the conditions, we don't need all the elements in this matrix. A lot of the elements are redundant. So MIMO radars using sparse sensing and matrix completion use exactly this idea. If you have a small number of targets, this delta matrix is low rank, so you don't need all its elements. So the receive antenna does not need to do match filtering with all transmit waveforms. It can use a random subset of these waveforms and obtain only a small number of samples and forward these samples. So the fusion center will start filling out this data matrix based on the elements that its antenna is using, and some elements will be missing. So the non-zero elements will correspond to the sample points. So somehow the fusion center needs to know the mechanism via which the antennas sample the target echoes. For example, they could be sampling based on a pseudo-random number generator, and the fusion center will know the seed of that pseudo-random generator, so it can fill in the matrix according to the sampling scheme. Because we know that this matrix is low rank, we can apply a matrix completion and fill it in. And once we fill it in, then we can give it to a standard array processing method to estimate the target. Now, the good thing about filling this matrix in is that, okay, when you do sparse sensing, you're collecting fewer measurements. So you have smaller signal power. But with this matrix completion, you're not losing in signal power. Eventually, it's as if you sampled at Nyquist rate. You're recovering all the missing elements. So the question is, can we indeed do matrix completion on this particular matrix? Because this matrix has a specific structure imposed by the geometry of the problem. So initially, we did simulations. We look at coherence bounds to see if indeed the coherence of this matrix is well behaved, is bounded. And here I show some simulation results. This is the coherence versus the number of receive antennas for different number of transmit antennas. And in all cases, you can see in simulations that the coherence is indeed bounded by a small number. And that number becomes smaller as the number of transmit antenna increases. So it drops to a small value. And this is the coherence as function of the distance between the targets. The coherence drops as the targets become more separated. And this trend is more pronounced as you increase the number of transmit and receive antennas. So this is just simulation results that gave us a hint that maybe this matrix can be completed. It has a good coherence. But we also did some theoretical analysis that validated these observations. I'm not going to go over the details of the analysis, but I will give you an interesting theorem that my student found somewhere in the literature that was essential in this analysis, just in case you want to use it. It says that if you have a matrix M that has real eigenvalues, then the minimum and maximum eigenvalues are bounded by these quantities. And these quantities depend on tau and S. So tau is the trace of the matrix, function of the trace of the matrix, and S square is the trace of the matrix square, and tau. During this analysis, we were able to show that the coherence of this delta matrix that I defined previously is bounded by these functions, and the minimum eigenvalues of these functions appear in the denominator. So applying that theorem, we were able to find some nice expressions for the coherence parameters. So we were able to show that if the number of targets is smaller than this quantity, then the coherence parameters, the mu naught and mu1, are given by these expressions. So the mu naught, you can see that if the number mi, so this is for I, could be transmit or receive a number of antennas, the m sub I. When the m sub I increases asymptotically, this tends to 1. So the coherence parameter tends to 1. So this scheme is asymptotically optimal. Now, the rest of the quantities that appear in these expressions, this depends on the distance between the two targets. As the two targets become come closer together, this increases, but it's well bounded. So as this increases, you can resolve less targets. This is a number of targets. The number of targets need to be smaller than a smaller number as the targets become less separated. So based on these expressions, we were able to explain the behavior that we saw initially via simulations, and plus understand more about the behavior of the matrix completion applied to the MIMO radar scenario. Let me show you some results here. In this scenario, we have two targets, 20 transmit, 20 receive antennas for the radar. And this is the probability of resolution as function of the minimum angle between the two targets. And I saw results for two SNR cases for 10 dB and 25 dB. And the solid line shows the probability when you use all samples of the data matrix, and the dotted line shows the probability when you undersample by 50% in this case. So in the high SNR case, both of them perform similarly. In the lower SNR case, interestingly, when you use 50% of the data, the probability of resolution is better than when you use all of the data. So the dotted line is the full data matrix result. So this actually was known because when you complete the matrix, it's like you're smoothing out the noise, right? You're rejecting a lot of noise by not using all the data points in the matrix, and by completing the matrix, you're smoothing out the noise. So the performance is a little bit better. And this is a probability of resolution. What is this? For a different scenario. This is a different transmit waveform. This is Hadamard waveform and orthogonal waveforms. So the type of waveforms that we transmit also matters. And you can actually optimize with respect to the transmit waveforms We have published another IEEE transactions on signal processing paper showing optimal waveform design. Now let me move to the optimum co-design problem for spectrum sharing between MIMO radars that use matrix completion, I call it MIMO MC radars, and MIMO communication systems. First, what is the motivation? So radar and communication systems may coexist and may interfere with each other. Already, the S-band radar that operate in the 2 to 4 gigahertz range interfere with LTE and WiMAX systems. And the Federal Communications Commission, FCC, and the National Telecommunications and Information Administration, and TIA, have proposed to release spectrum in the 3.5 gigahertz range that was traditionally used for defense applications, for radar applications. This hasn't happened yet, but it's going to happen soon, creating a big problem of interference between radar and communication systems. And some approaches that have been used to avoid interference is to exploit large spatial separation. There was a report by NTIA, and this shows the radar exclusion zones which exclude commercial use so that one avoids interference with radar systems. So this is a graph from that report. Another type of approach that has been used to avoid this interference is use dynamic spectrum access using spectrum sensing, time division multiplexing, frequency division multiplexing. Still, this might not be a good approach, not a bandwidth efficient approach. Now, another class of techniques are based on spatial multiplexing. If there are multiple antennas on the radar and the communication system, then you can actually multiplex the two signals and control the interference in this way. So what I'm going to talk about next falls under this last category of spatial multiplexing. The MIMO radar and a MIMO communication system do have multiple antennas that can be used for this purpose. Now, prior work in this area have designed radar waveforms that are projected to the null space of the interference channel. So you project to the null space of the channel between the radar and the communication system. So the radar does not cause any harm to the communication system. However, if there's a target close to the communication system, you will miss the target by doing this kind of projection. You're not going to get any returns from the target. So it's not necessarily a good approach to do this kind of null space projection. Let me describe the model for the spectrum sharing scenario for our work. So this is a MIMO radar, collocated MIMO radar system. And this is a communication system. These are the MIMO communication system. These are the communication antennas. These are the transmit antennas. And these are the communication receive antennas. And these are channels. The H is the channel between the communication system, transmit and receive antennas. And G2 and G1 are channels between the communication system and the radar system. We will assume, for simplicity, that these are flat fading channels and somehow can be estimated and shared with the communication and the radar system. We also assume that the fading is block fading, so it does not change very fast. It stays the same for L symbols. The radar and the communication system transmit pulses we'll assume that these pulses are synchronized. So if you look at the radar receiver, the radar receives this echo that is due to the transmitted pulse by the radar. And then it also receives this gray area that is due to the communication system transmitted signals. So the gray area represents the interference that the radar system sees. The radar system is only interested in this echo. This is the target echo. And the radar transmission repeats after a certain time interval, the partial repetition interval. If we look at the communication receiver receives the communication signal, which is interested in, and the contribution of the radar during transmission. Right? This is the interference that the communication system sees. Mathematically, if you forget for a minute about this omega quantity, the fusion center will formulate this data matrix, YR. And this data matrix can be expressed as a signal component. This is a signal component that contains basically the target echoes. This is what the radar is interested in, this component. But it will also contain the interference due to the communication signal transmission. The communication signal transmits these X waveforms. So this is the interference and also some noise. The communication receiver will transmit the signal it's interested in and the interference due to the radar. So these are the radar waveforms. This is the interference due to the radar plus noise. Here we assume that the channels that appear are estimated and fed back to the communication transmitter. Now, the communication system can obviously reject some of the interference of the radar. It can monitor the radar and try to reject some of the interference. The simplest way would be to do some direct subtraction. However, because of frequency offsets of the two systems, it will not be able to subtract interference 100%. So there will still be, despite of the attempts to subtract some of the interference, there will still be interference because of the radar at the communication receiver. If you look at the interference that is caused by the radar at the communication receiver, you can express it in this form, where S is the contribution of the radar. And because the radar transmits different pulses, L is the pulse index, this interference changes from pulse to pulse. It's the covariance of the interference. L is the pulse index. So the interference is time varying. So the communication system should design its waveforms such that its rate changes to accommodate this time varying interference. So it should do adaptive transmission. Now let's look at our design constraints. The communication system has certain power budget, and the power of the communication system, we're going to use L pulses, is the sum of the trace of the covariance of the transmission signal. So this should be less than some threshold here. And we want the average communication rate to be greater than a certain threshold C. So we want the communication system to meet certain communication rate. So this is the rate. It's the average over L pulses. And this represents the rate in its pulse. Now, if we look at the, forget about the subsampling. If we look at the interference exerted at the radar receiver, the total interference looks like this because of the communication system over L pulses. Now, if the radar does sparse sensing, then the interference will appear only in the samples that are sampled, in the data samples points that are sampled. So if this is the communication system, this is the radar receiver, and the radar subsamples, then this subsampling changes from symbol to symbol. So effectively, the channel between the radar and the communication receive antenna changes, effectively changes. It's not the same. So instead of using this kind of measure for the interference, when the radar implements random sampling, we can use this effective interference that uses the fact that the channel changes from symbol to symbol. So this is the difference between these two. So this is the effective interference because of the subsampling that the radar does. Now, we're going to design the two systems so that we minimize the interference of the radar, subject to meeting power and rate constraints at the communication system. I'm going to formulate two different problems. The first problem, for comparison, is when the way that the sampling is done at the radar is not known at the communication system. So if the communication system does not know what kind of random sampling the radar does, it can only try to design its covariance matrices based on the total interference power, as if no random sampling was done. So we can formulate this problem and solve it. In this case, the radar works as a typical MIMO radar without doing any sparse sensing. Now, if the communication system knows the random sampling that the radar does, omega, so omega is a matrix that contains the points that were sampled, then we can formulate a different optimization problem, P1, where we optimize the effective total interference. So the effective total interference takes into account the interference at the sampled points. And again, we want to minimize the total interference subject to power and rate constraints on the communication system. The unknowns here are the covariances of the communication system during the capital L symbols that we consider. This is a convex problem, but it's computationally demanding. But we have proposed an algorithm based on dual decomposition that is based on the fact that the objective and the constraints are separable functions of the covariances of the communication system. We have shown that between the two problems, the problem that takes into account is based on the random sampling achieves smaller interference. And here's the idea why this is happening. So this is the communication system, this is the radar system, and this is the channel between them. As I said, when you do random sampling at the radar receiver, effectively, this channel changes, and it changes from symbol to symbol. If you look at the null space of this channel, this is probably empty, right? The null space of this channel is empty. But the null space of this channel is not empty. So this gives the communication system the possibility to design its transmission so that it falls in the null space of this channel, so it does not cause interference to the radar system. So this is where the advantage of the MIMO radar with random sampling comes in. By effectively changing this channel, modulating this channel, so that it has a non-zero null space that gives the opportunity to the communication system to design its transmission in a way that minimizes the interference to the radar system. And now a third type of problem for spectrum sharing. Suppose that the communication system knows, suppose that the sampling scheme is not fixed, but it's jointly designed along with the covariance matrices of the communication system in order to optimize, to minimize the interference to the radar. So it's a more involved optimization problem. We want to minimize the effective interference. And the minimization variables are the capital L covariance matrices and the sampling scheme of the radar. Subject to these constraints, power and rate constraint. And of course, when you do a random sampling, we want to make sure that this matrix, the sampled matrix, has certain properties. So initially, the sampled entries should be uniformly distributed in the matrix. So this is one constraint. More recently, it's enough for this matrix to have large spectral gap. The spectral gap is the distance between the largest and the second largest singular values. So if the gap is large, then the sampled entries do not have to be uniformly distributed. So these are some properties of this delta matrix. So this problem is not convex. We solve it using alternating optimization. So we solve for the covariances, having fixed the sampling scheme, and then we solve for the sampling scheme, having fixed the covariances. And still, these are difficult problems. Maybe some, the details can be found in the paper. So this is a simplification. Obviously, these optimization schemes involve a lot of complexity. We can simplify the complexity by allowing the communication system to transmit at two different rates. One rate during the radar transmission and another rate when the radar does not transmit. So this is the P1 prime problem that we can set up. So basically, we have fewer parameters to optimize with respect to. It's a simpler problem. And this is the complexity of the different schemes that I described. So the constant rate, which is this scheme, we only need to optimize with respect to this matrix. The most involved scheme is the joint design scheme, where we need to optimize with respect to the capital L covariance matrices and the sampling scheme. And obviously, the complexity is higher. Just to show you some results on how the adaptive rate of the communication system helps reduce the interference at the radar receiver. So the dotted lines here correspond to constant rate communication system, and the solid lines correspond to adaptive rate. In all cases, I'm showing the interference caused at the radar receiver as function of the sampling rate that is performed at the radar receive antennas. And it's obvious that the adaptive rate schemes do better. So this is, for the adaptive rate schemes, this is a selfish communication system that optimizes its transmission, adapts its rate, and optimizes its transmission in order to minimizes its power and meets a certain power constraint with no regard about the interference it's causing. And when we do the cooperative scheme, obviously the effective interference power is smaller. We can see that the effective interference power increases as the subsampling rate increases. When the subsampling rate is 1, this MIMO, this is a spectrum sharing between a typical MIMO radar that uses all the samples of the data matrix. So it's interesting to see that the interference increases as we're using more samples. And this is because, as I explained before, the null space of the channel becomes smaller, so the communication system has less opportunity to design its waveforms to interfere less with the communication system. That's why we see the interference increasing. Of course, it doesn't mean that we want to subsample as much as possible to, let's say, retain only 40 or 30% of the samples, because then we won't have enough samples, although we won't have enough samples to do matrix completion. So this is the relative recovery error for matrix completion as function of the subsampling rate. Again, this is the cooperative scheme. We can see that there is an optimum subsampling rate occurring around 0.7. So if we retain 70% of the samples, then we get the best recovery error. And the cooperative scheme is better than all the other schemes that we compared against. I'll make sure I don't go over time. So this is the CPU time. All schemes are have high complexity. Just to give you an idea, this is the CPU time in seconds as function of the waveform length L, how many symbols, how many pulses we use in the estimation. And this is the joint design scheme where we design the covariance of the communication system and the sampling scheme of the radar. And another comparison, this is for a radar system that has 4 transmit and 4 receive antennas, and the communication system that has 8 transmit and 4 receive antennas. And I show the effective interference power as function of the subsampling rate for the different schemes. This is the joint design scheme, when we can clearly see it's better than the selfish communication. The selfish communication causes a lot of interference to the radar receiver. And this is the relative recovery error of the matrix completion as function of the subsampling rate. Again, one can see that there is an optimum subsampling that should be performed at the radar, around 60%. And the joint design performs better than the other schemes in this case. So to conclude, I presented a sparse sensing MIMO radar scheme that uses matrix completion to recover basically the samples, the data points that are not sampled, and showed that it's a good candidate for spectrum sharing because the way it modulates the channel, the random sampling, it performs better than the regular MIMO radar. MIMO MC radars are good candidates for network radars because they, by random sampling at the receive antennas, you use smaller number of data points. This means that you have to transmit fewer data points to the fusion center, and this means less communication power and less communication bandwidth. And I guess I will conclude here. We have done more follow-up work on this, where we also use pre-coding at the radar and the communication system, and we optimally design the pre-coding. And this kind of pre-coding allows us to avoid clutter. If we know that in certain places there is clutter, we can design the beam in a way to exclude clutter. Yes, so I will stop here and try to answer any questions. Yes.
If you go back to the probability of detection in the MIMO radar case, where you show that the matrix completion operation is improving detection performance.
Probability detection.
Way back.
Yeah.
Yeah. I'm trying to understand whether, what, can you give some intuition for what the matrix completion operation is doing? Is it spatially filtering, temporally filtering, or both?
Spatial filter, yeah.
And so that's the reason for improved performance in the moderate SNMI case.
Right.
It's like interpolation.
So I'd like to ask a follow-on question on that. Since you're doing interpolation, you're not actually adding information.
No.
And so the question is, could you go directly from that rather than doing matrix completion? Or is it the fact that you're changing your sampling every time, you can't learn how to go directly from the sampled data?
It's not straightforward how you could use these small number of elements to do what you want to do. I'm not aware of any work. Maybe you can do it, but I don't know how you would do it.
I have the deep learning bias of you can do anything with deep learning.
It's possible that you can use deep learning, yes.
Other questions?
That was one of the questions that the reviewers asked for the paper before we submitted it. But it's not obvious how you would do that. Right?
Yeah, I think the fact that it's changing randomly from time, you're changing it randomly from pulse to pulse, right?
Mm-hmm.
Yeah, so that's the problem that I wouldn't know how to deal with. But otherwise, you could probably learn something about, I don't know.
Yeah,
It's an interesting
It's a good
question.
problem to look into, yeah.
That's an interesting question. Okay, last chance. All right, we'll thank our speaker.
Thank you.